We are Creighton University, and today we'll be presenting our unique proposal for the Cheyney University use case. There we go. We will start by introducing our team. I am Max Markson Prince, and I'm assuming the role of the project manager. With us today, we have Ashley Nelson, our financial analyst, Emma Goldsmith, our project developer and environmental analyst, and Alex Weber, our engineer and system designer. We'd also like to thank Dr. Ange Baruth, our team advisor.
To top our efforts between team members, we'd like to give a special thanks to notable industry advisors who are key in ensuring our assumptions were compliant with both industry professionals and best development practices.
Look, this particular use case was a difficult challenge. Low rates, low endowment, environmental and physical constraints presented us with limitations that made this use case invigorating. We realized that taking a strategic approach that is sensitive to these challenges will advocate for a prudent, exciting solution. In this proposal, we pursued a four-pronged approach to develop a reliable, renewable, and resilient solution for Cheyney University. These are the use case's main issues, and our proposal is going to solve them.
To reach these goals, we established a sensible, achievable strategy that will help guarantee a sustainable financial model for Cheyney throughout this project. Shock payments from a loan to finance is really not an option, but we have a practical solution. We determined that a 25-year PPA agreement with 5.31 cents per kilowatt hour energy charge is the best solution for Cheyney to bring a solar array to campus. This is a very low but competitive PPA price. Based on advice from our local power district and historical energy pricing, a 2.5% annual escalation rate will be proposed for this PPA agreement. With the volatility of the energy market, this PPA will provide something incredible, a hedge on energy prices and 25-year budget security. Due to the importance of the established relationship with Pennsylvania Electric Company, we recommend that net metering not be used for this project, but I can assure you we found an even better solution. In order to reach the goals of the developer and Cheyney, the modified internal rate of return will need to be close to or greater than the weighted average cost of capital. We also want a positive net present value for system owners and recommend giving priority sale of renewable energy credits to PECO. If Cheyney wants to become the owner of the system sometime in the future and retain the RECs, we recommend that RFP include buybacks and the possibility of a partnership flip as described in the development plan if a donor or capital campaign was to materialize. For Cheyney University, we desire a solution to create positive and consistent endowment growth model. As we move through the proposal, you will see how our recommendations make every single one of these things possible.
In order to choose the best possible locations for our solar arrays, we analyzed environmental conditions on Cheyney's campus. We intentionally chose locations away from floodplain zones, locations with optimal soil quality, and locations away from steep slopes, which may result in hill shade and decreased solar resource. In order to account for our proximity to the floodplain and a slight overlap of lower soil quality regions, we plan to introduce gravel into these areas of our ground arrays. In addition to these physical constraints, we accounted for the fire, building, and electric codes on a national and local level. So this was a challenging site, but we were able to identify 3 locations that met our environmental constraints, reach convenient interconnection spots, and accommodate for aesthetics and visibility on campus. The 3 locations that we chose to focus on are the Science Center green space, the Duckery building, and the treatment plant green space.
Now that we know the optimal locations for the arrays, we must identify how proposed arrays are best sized with the campus energy load. Average provided load data for 8 buildings on campus, which accounts for 25% of the total campus load, shows variability of campus energy usage throughout the day. For the entire campus, the minimum demand is around 1 megawatt. As you can see, the highest demand is during the late evening at around 11 o'clock p.m. When sizing the array, we will not be focusing on these peaks, which are central to the demand charges. So instead, we will size the arrays to mitigate energy rates throughout the daytime. One thing that we must consider an array also is energy demand fluctuation around certain campus or weather events that may pose an outage threat. By incorporating a battery system in some of our design, we add resilience for anomalies like these. So overall, look, we have identified 3 locations for solar development: Science Center, the Duckery building, and the treatment plant. In addition, we've also considered the energy bill being low for Cheyney University due to their unique relationship with PECO, but we have financial strategies that make solar investment achievable for them. In addition, we have found a proposed PPA that works for both the investor and Cheyney University. Also, we account for campus demand fluctuation throughout the year. These are the challenges that we are going to solve, starting with strategic design via a tiered approach.
As we assess the duct rebuilding rooftop for PV integration, a priority was to maximize offset of load consumption. We decided an elevation tilt angle of 10 degrees will maximize power density for the building while minimizing potential hazards from wind. While modules oriented at an azimuth of 180 degrees has the greatest annual production, the figure on the left shows that by assuming an azimuth of 225 degrees southwest, our modules will deeper penetrate load consumption into peak demand time with minimal annual losses. For the duct rebuilding rooftop, this azimuth was further justified by the natural orientation of the building, allowing for the greatest power density at an azimuth of 225 degrees southwest. We concluded to pursue single axis tracking arrays for our two ground mount systems, the Science Center array and the treatment plant array. Axis tracker limits were determined through elevation and azimuthal angle matrices shown on the left. We resolved a rotational tracker limit of 45 degrees will optimize our ground mount systems for year-round generation. The Science Center array is designed to follow the 5-degree incline slope it sits on, oriented 135 degrees southeast, optimizing generation for the afternoon load. The treatment plant array is oriented 180 degrees south to maximize annual production, add resilience, and peak shaving throughout the assistance of battery storage. The interconnection of our arrays directly into nearby distribution nodes will allow for the aggregation of the energy produced to best offset total campus load. Utilizing Cheyney University's heat map, seen on the left, we ensured our points of interconnection had sufficient hosting capacity to accept the generation from each of our arrays. Our array's total aggregate production was designed to stay under Cheyney's 1 megawatt AC daytime minimum load limit to avoid the net metering of exported generation. The Science Center array has a generation capacity of 347 kVA, the duct rebuilding array 252 kVA, and the treatment plant array 277 kVA, all of which are well under the limit of their interconnection nodes. For these reasons, we will interconnect our arrays directly into nearby distribution nodes. Our Tier 1 proposal includes the duct rooftop array and the Science Center ground mount array. With the addition of the treatment plant array and battery storage in our Tier 2A and 2B proposals, the net generation totals 941 kilowatts DC and 790 kilowatts AC. These arrays were designed to best meet Cheyney University's goals.
All right, great. Alex has found a great design for us, but what we needed to think about then is how the systems operate in accordance with campus demand. The Tier 1 option, which incorporates just the Science Center and duct rebuilding arrays, is designed to best mitigate loads during the daytime, cutting energy rate costs. The Tier 2A option, which incorporates just the treatment plant array, is designed for consistent, more resilient generation throughout the day. Both of these options will be combined with battery storage to form the Tier 2B option. When we incorporate a battery system in option Tier 2B, we see a significant shift for system resiliency. As described in our conceptual system design document, the battery system will be incorporated into the treatment plant array. Option Tier 2B has a considerable energy load reduction that optimally charges the battery throughout the day and mitigates demand charges in the late evening. On average, we are looking at a daily reduction of about 66 kilowatts during the demand peak hours. With this system, 8% of the entire campus load is mitigated throughout the year. Pictured here are the cost analyses for the Science Center array and the duct rebuilding array for the Tier 1 option. As noted in our development plan, this project occurs within an 8-month construction window. Pictured here are the cost analysis for the treatment plant array in the Tier 2A and 2B options. When we consider battery storage in the 2B option, the costs are significantly higher. But based on the cost projections from an NREL report in 2018, we propose the best solution based on financial feasibility and climate action response would be to pursue a battery system in the year 2030.
Here are the raw numbers for the cash flows for the proposed project, but let me tell you their story. Tier 1 is highlighted in green, 2A in blue, and 2B is highlighted in purple and orange. You can see in the chart that we have identified if this is a good investment or not. In looking at this chart, you can see that the investor has a positive net present value in nearly every project here. As you can see, battery today is not a financially great opportunity for the developer, but we're going to tell you why it's a great idea and would be more reasonable in a few years. Each of the projects also has a competitive investment status with a modified internal rate of return above or right above right below the weighted average cost of capital.
Customer savings in the PPA over the 25-year period are negative. However, despite these seemingly low values, in a minute, we will show you that this does not hinder Cheyney University's room for endowment growth whatsoever, which is highlighted initially in our requirements for the PPA. In comparison to a cash purchase of these arrays, a PPA option provides greater long-term stability for Cheyney's endowment.
Our PPA price is 5.31 cents, which may seem low, but let's break it down to show how this price can still make the developer money with a reasonable weighted average cost of capital. In deciding the capital structure for the developer, we cited NREL and industry standards for a 50% debt and 50% equity structure. This structure was utilized in our weighted average cost of capital calculation, and as seen in our develop plan, gave us a WACC of 5.18%. This number is consistent with industry standards, and based on conversations with industry professionals, this WACC well assesses the risks and rewards of the project. As previously mentioned, renewable energy credits are an imperative piece of our proposal. As illustrated in our development plan, selling RECs allows for a much faster, positive project cash benefit. Now, selling RECs is not only financially important, but it also provides a great way for Cheyney to give back. If the developer were to sell RECs, we recommend giving PECO first bidding priority. This allows the utility, and in turn, the state of Pennsylvania, to increase their renewable energy portfolio. The modified internal rate of return is a much more powerful financial tool than the internal rate of return. By assuming that positive cash flows are reinvested at the firm's cost of capital and initial outflows are financed at the financing cost, the MIRR is able to paint a way more realistic picture of how cash flows are actually pumped back into the project. In order for the project to be seen as financially viable, the MIRR should be competitive with or greater than WACC. For the recommended Tier 2B, the MIRR is highly competitive with WACC, which is just another great sign for the developer.
Looking at the customer savings in the PPA, we can find in our cash flow analysis, we show that the PPA options are actually a fantastic suit for Cheyney University. Looking at the national average 8% annual university pre-pandemic endowment growth, we see that the PPA options have very little effect on Cheyney University's endowment. In fact, Cheyney University's endowment shows consistent positive growth under PPA agreements in comparison to cash purchases. This key point is highlighted in the requirements for our proposed PPAs.
After all is said and done, our team put together this project with one goal in mind: sustainability. Cheyney University could pioneer the evolution to a sustainable future. This project alone has the potential to make tremendous bounds towards an environmentally friendly world, both through its direct impact shown on this slide and the precedent it can set. Additionally, based on a discount rate agreed upon by almost 200 economists, this project will save the planet $2.3 million, the true value of carbon.
So, in conclusion, Cheyney University has a clear vision, a new trajectory, a new spark for innovation, a new Cheyney. But innovation is nothing new to Cheyney. As the nation's first HBCU, this has been their hallmark for over 180 years. Low rates, low endowment, environmental and physical constraints presented us with limitations that made this use case invigorating. That being said, we realized taking a strategic approach that is sensitive to these challenges will advocate for a prudent yet exciting solution. We propose that it is best for Cheyney to go into a 25-year PPA agreement set at 5.31 cents per kilowatt hour with 2.5% escalation. In this time of Cheyney's dedication to innovation, we are not promoting business as usual. Instead, we are proposing actionable change that is reliable, renewable, and resilience. It is reliable. We knew we had to focus on getting competitive rate of return to attract the investor developer. We've shown several solutions where the modified internal rate of return exceeds the weighted average cost of capital. It is renewable. We've designed and optimized several PV systems that Cheyney can pursue that will directly impact their climate action goals. It will mitigate $2.35 million of the social cost of carbon. It is resilient. This proposal hedges against the future volatility of energy prices. We're presenting Cheyney with a known, reliable energy cost for 25 years without detrimentally affecting its endowment. This is our vision for a new Cheyney. Thank you.